In this video, we're going to talk about circular motion, which will be angular velocity and linear velocities. This will go in with being able to use radians appropriately, and that was covered in our first video. For a circle of radius r and a central angle theta, an arc of length s has a length given by s equals r times theta. Theta must be in radians. Let's jump into an example. Find the length of the arc intercepted by a central angle of 240 degrees and a radius of 4 inches. So let's think about, let's think about a circle that's got that kind of an angle cut out in it. 240 degrees would, and this is again, it's just approximation, it would be this part. For the arc length, we're actually looking for this part. How long is that arc? First, notice that the angle is given in degrees. That has to be converted to radians immediately. 240 degrees times pi over 180. 240 over 180 reduces to 4/3. So 240 degrees is equal to 4/3 pi. Now whatever length your radius is given, that's fine. It can be any length. Multiply that by your central angle in radians. 4 times 4 pi over 3, that gives you 16 pi over 3. And if you use that in a calculator, that'll give you just shy of 17 inches. So this arc marked in red would have an approximate length of 16.76 inches. Okay, so that's arc length. This angle in here was your central angle, and it has to be in radians. The radius of 4 inches, that's each one of those. Okay, so let's move to the next topic. Consider a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed of the particle is arc length divided by time. Linear speed is denoted with a v, and that's equal to s over t. Basically, in this diagram, it's how fast the object is moving around the edge of the circle. Moreover, if theta is the angle in radians corresponding to the arc length s, then the angular speed, which is denoted with an omega, it looks like a W. It's just got a smooth round bottom. But the angular speed of the particle, omega, is given as the central angle swept over time. Let's also note that linear velocity can be calculated by radius times angular velocity. Let's do an example. The second hand of a clock is 10.2 centimeters long. Find the linear speed of the tip of the second hand as it passes around the clock face in centimeters per second. In one revolution, the arc length traveled is 2 pi r. Remember, that's the circumference of a circle. So one revolution, 2 pi times the radius given, which was 10.2 centimeters, is 20.4 times pi centimeters. The time for one revolution is a minute or 60 seconds. We were asked to find centimeters per second. The linear speed of the tip of the second hand is going to be the arc that gets swept, 20.4 pi centimeters divided by 60 seconds. That's how long it takes to make a full rotation. Gives us an approximate speed of 1.07 centimeters per second. Another example, the blades of a wind turbine are 116 feet long. The propeller rotates at 15 revolutions per minute. Part A, find the angular speed of the propeller in radians per minute. Radians per minute. Okay, so we're given that it rotates at 15 revolutions per minute. One revolution is equal to 2 pi radians. Your revolutions cancel, and that will leave you with 30 pi radians per minute. That's the angular velocity of the wind turbine blade. Part B, find the linear speed of the tips of the blades. Linear velocity is arc length traveled over time. Well, arc length is defined by radius times central angle divided by time. The radius is a 116 foot long blade spinning at 30 pi radians per second. Remember from the previous slide at the very bottom, V can be also calculated with R times omega. We just calculated omega. R is given in the original problem. And so that calculates out to approximately 10,933 feet per minute. So that's moving pretty fast. The area of a sector, we have A equals 1/2 times the radius squared times the central angle in radians. A sector of a circle is the region bounded by 2 radii of the circle and their intercepted arc. Think of it as a slice of pie or cake, much like our diagram earlier. So take a circular cake or a pie, cut out a slice. That slice is called a sector. The length of your cut is your radius. The angle inside, that's your central angle. Make sure it's in radians if it's not given in radians. And this is your formula to calculate the area of that sector. Let's look at an example. A sprinkler on a golf course fairway sprays water over a distance of 70 feet and rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. So I tried to draw a little diagram to illustrate what's going on here. So we have a 70-foot stream back and forth over a 120 degree central angle. Well, that's degrees, so immediately convert that to radians. 120 over 180 reduces to 2/3 pi. The radius was given, 70 feet. So the area that is watered is 1/2 times the radius squared times the angle in radians. 70 squared, that's 4,900. These twos cancel, so 4,900 pi divided by 3. If you put this in your calculator, that's approximately 5,131 square feet of fairway that gets watered by this particular sprinkler. A second example, the diameter of the drum of an electric hoist is 8 inches. When you're logged in doing your homework, you'll have an illustration of this particular problem. I didn't draw a diagram because I can't draw very well, and I knew you'd be able to see the diagram in your homework. Find the number of degrees through which the drum must rotate to lift a beam 2.5 feet. 2.5 feet, there's 12 inches in a foot, so 2.5 times 12, that gives us 30 inches. Now, why am I doing that? The diameter of the drum was given in inches. The lift is given in feet, so I wanted to compare apples to apples. I converted feet to inches, so now that we're inches all the way through, each turn of the drum is pi times the diameter. Now, why am I using that formula? If you double your radius, you get the diameter. This D serves as a 2R from up here. So pi times diameter is the same as 2 pi radius. That's going to be 8 pi inches. The diameter is 8 inches, so we just simply plug an 8 in. That's 8 pi inches. It's going to take 30 divided by 8 pi rotations to make the total lift of 2.5 feet. So the total lift divided by 8 pi, which is the distance covered in one rotation of the electric hoist, that tells us that we have 1.1937 rotations that drum must make. Each rotation has 360 degrees, so it's got to go 400, just shy of 430 degrees in order for that drum, which is the girthy part of the electric hoist, to raise a beam 2.5 feet. Let me know if you have any questions. Send me an email. If we're back in a traditional setting, ask in class. We can work more examples.